Usually when we think about gravity, it's not exactly like a grand cosmic mystery. It's an annoyance.
Right, yeah. Mostly just an inconvenience.
Exactly. You're holding a perfectly good sandwich, you trip, you drop it, and, the dog gets it. It's just this mundane, everyday reality that we all live with.
Well, because it's entirely terrestrial. I mean, our brains evolved to handle the physical world doing exactly what it always does right in front of us. So we rarely stop to question the actual mechanics of it.
But today, we are taking that falling sandwich and using it to launch into the absolute cutting edge of human knowledge. Welcome to today's deep dive.
Glad to be here.
We are promising you a shortcut to being well-informed on what reality is actually made of. Our mission is to start with that dropped lunch and travel all the way to the mind-bending mysteries of dark energy, antimatter, and, well, the fundamental rules governing the cosmos.
It's a wild ride.
It really is.
Yeah.
And our source material today is an in-depth conversation featuring Don Lincoln. He's a veteran particle physicist at Fermilab, which is one of the premier physics laboratories in the world.
And, if we connect this to the bigger picture for a moment, it's really easy to assume this is all just abstract math, like stuff that doesn't impact daily life.
Right, like why should I care?
Exactly. But look back, say, 150 years. Scientists were just playing around with magnets and sparks in laboratories, and people at the time understandably asked, why bother?
Their question.
But that basic, curiosity-driven physics research gave us the electrical grid.
Wow.
It gave us the internet. So the mysteries we are exploring today, the very fabric of space-time, the behavior of subatomic particles, these hold the keys to limitless energy, to interstellar travel, and fundamentally to our understanding of why existence itself is here.
Okay, let's unpack this. To understand the bizarre frontier of modern physics, we first have to understand the foundational strategy of the entire field. And that strategy essentially boils down to a single word, which is unification.
Yeah, unification. For centuries, the holy grail of physics has been to prove that wildly different, seemingly disconnected phenomena in the universe are actually just different faces of the exact same underlying rule.
Like shrinking the rule book.
Exactly. We want to shrink the rule book of reality down to as few pages as possible.
And this goes right back to that drop sandwich in the 1650s. Isaac Newton is sitting there, and he has this profound realization that the gravity making an apple or a sandwich fall to the earth is the exact same force keeping the moon in orbit around the Earth.
Which is a massive deal at the time.
Right. Because before that moment, people literally thought there were two completely different laws of physics. They believed there was terrestrial gravity for us down here and this, magical celestial gravity for the heavens.
And Newton unified them.
Yeah.
He demonstrated mathematically that they were one and the same mechanism. And that pattern of unification really became the blueprint for all of physics. If you jump ahead to the 1860s, you have a lightning bolt tearing across the sky, and you have a little iron magnet sticking to a piece of metal.
Visually, totally unrelated.
Absolutely unrelated. But James Clerk Maxwell took 50 years of previous experimental ideas, people like Michael Faraday playing with coils of wire, and he unified them. He wrote the equations of electromagnetism.
So he mathematically proved that the electricity of the lightning and the magnetism of the iron are the exact same force.
Yes.
But what I find so fascinating about Maxwell's work is the byproduct. When he combined those equations, it created a wave equation. And when he calculated the speed of that electromagnetic wave, it perfectly matched the speed of light.
Right, and what's fascinating there is that the speed of light wasn't just a property of light anymore.
Oh, interesting.
Maxwell showed that the speed limit was baked into the fundamental rules of electricity and magnetism. Light itself was just a ripple in this unified electromagnetic field.
Okay, I see.
And that realization set the stage for perhaps the most famous unification of all. Albert Einstein and his teacher Hermann Minkowski in the early 1900s. They took space, the three dimensions we move through in time, and unified them into a single woven fabric called space-time.
Now wait, I have to push back on this space and time equivalence.
Sure.
Because in my everyday human experience, I can walk across the room to the fridge in space, and then I can just turn around and walk right back.
True.
But I absolutely cannot walk back to yesterday in time. So how can physicists claim they are the exact same fabric if I can move freely in one direction, but I'm relentlessly dragged forward in the other.
That visceral reaction you're describing, that is the exact reaction everyone had in 1908. It runs completely afoul of our evolutionary intuition.
I'm not the only one.
Not at all. But the mathematics showed that one person's experience of space and time is intrinsically linked to another's based on how fast they are moving relative to one another. And that speed of light we just mentioned, it turns out it's simply the universal speed limit of movement through this unified space-time fabric.
So it's not about the light itself.
Exactly. You can think of it like a property of space itself, a maximum capacity for transmitting information from point A to point B. It feels counterintuitive at first, but cultural familiarity eventually makes these wild leaps seem obvious.
What do you mean?
Think about how we view atoms. We tell toddlers the solid world is mostly empty space made of invisible atoms, and they just accept it.
Yeah, that's true.
Eventually, navigating the concept of spacetime will feel just as intuitive to us.
That sets up our next major hurdle, though. Einstein unified space and time, but by the 1930s, physicists were realizing that the universe was still incredibly messy.
Very messy.
They discovered 4 completely disconnected fundamental forces governing reality. You've got gravity, electromagnetism, the strong nuclear force holding atoms together, and the weak nuclear force responsible for radioactive decay.
Right.
So following Newton and Maxwell, the new mission was to unify these 4 forces.
And by the 1960s, scientists made a major breakthrough on that front. They successfully proved that electromagnetism and the weak nuclear force were mathematically the exact same thing at extremely high energies.
The electroweak force.
Yes, the electroweak force. But this breakthrough came with a massive, glaring contradiction.
A seemingly theory-breaking glitch.
Yeah.
Because electromagnetism has an infinite range. That is why you can look up into the night sky and see starlight from a galaxy millions of light years away. The photons carrying that light travel forever. But the weak force, it is practically trapped inside the microscopic nucleus of an atom.
Right. And to understand why this was such a huge problem, we have to look at how forces work on a quantum level.
Okay.
In particle physics, forces are carried by messenger particles called bosons. Electromagnetism is carried by photons, which have absolutely zero mass, allowing them to just zip through the universe indefinitely.
Makes sense.
The weak force, however, is carried by particles called W and Z bosons. And unlike photons, W and Z bosons are incredibly heavy.
Heavy at a subatomic level.
Yeah, massively heavy. Because they are so heavy, they require huge amounts of energy to even pop into existence. They burn out and decay almost instantly, which means they can't travel far. The force is trapped.
So the question was, how can a force with infinite range carried by massless particles be the exact same thing as a force trapped inside an atom by massively heavy particles?
Exactly. It threatened to tear the whole unification theory apart. To save it, physicists in 1964 had to introduce a massive theoretical patch.
Enter the Higgs field.
Enter the Higgs. The theory proposed that there is an invisible field permeating all of empty space everywhere in the universe.
Everywhere.
Everywhere. And the rule of this field is simple. Particles that interact with it get bogged down, and that interaction is what we perceive as mass. Particles that naturally ignore the field, like photons, just sail right through with zero mass, traveling at the speed of light.
I love this specific analogy from Don Lincoln's source material to help visualize this mechanism.
Oh, the gravity one.
Yeah. Imagine an invisible gravity field right in front of you. If you hold a heavy pen and drop it, it falls.
Why?
Because the pen interacts with that field.
Right.
Now imagine you put a completely massless object right in that exact same spot. It doesn't fall. It just floats there, completely unaffected. That is basically what the Higgs field is doing to particles as they try to move through space.
It's a staggering reality to wrap your head around. I mean, it implies that empty space is not actually empty. The Higgs field has a non-zero value everywhere.
Wow.
It is fundamentally what endows our universe with mass. Without this field dragging on particles, everything would just zip around at the speed of light. Atoms could never form, stars, planets, you and I simply would not exist.
But theories and beautiful math equations are one thing. In physics, you actually have to prove them in the real world.
Right, you need experimental proof.
And to prove that this invisible Higgs field actually existed, humanity had to build the most complex, gargantuan machines in history, which are particle colliders.
And this relies on Einstein's famous equation, EMC-HOR, which tells us that energy and mass are interchangeable.
Usually we think of that with, like, nuclear weapons.
Exactly, where a tiny bit of mass releases a huge amount of energy. But in a particle collider, physicists use it in reverse, like a creation engine.
How does that work?
Well, if you take two particles and smash them together with massive amounts of perfectly balanced kinetic energy, the forward motion stops. All that raw energy has to go somewhere, so it literally converts into entirely new mass. It creates new particles out of the sheer force of the impact.
And this sparked an intense, friendly rivalry between Fermilab, with their Tevatron collider outside Chicago, and CERN, with their Large Hadron Collider over in Europe.
The LHC.
Yeah. They were in a race to smash particles hard enough to excite this invisible background Higgs field and essentially knock loose a physical piece of it, the Higgs boson particle.
And the sheer scale of the LHC is almost beyond comprehension. You have two colliding beams, each thinner than a piece of spaghetti, racing in opposite directions around a 17-mile underground ring.
17 miles.
Yes, and when those thin beams cross paths, they create a billion subatomic collisions every single second.
A billion a second. And the detectors acting as cameras for these collisions, they're the size of a 5-story building.
They're massive.
The CMS detector weighs 14,000 tons. And it is attempting to take 40 million pictures a second.
That's unbelievable.
But here is my logistical pushback. If there are a billion collisions a second, and the vast, vast majority of them are just boring, established physics that we've known for decades, how on earth do you find the one next Nobel Prize particle in that haystack? It seems like an impossible data problem.
It really does. It requires an unbelievable feat of computing and automated filtering.
Okay, so how do they do it?
Physicists built fast electronics that act as hardware triggers. Out of those 40 million pictures a second, the hardware instantly throws out the junk and filters it down to about 100,000 events that look vaguely interesting.
Still a lot.
Right. From there, massive server farms run quick analyses and filter that down to about 1,000 collisions a second. Only those 1,000 are actually recorded to permanent storage.
And then humans look at it.
Yeah, armies of graduate students painstakingly pore over that filtered data. They analyze the trajectories and energy signatures of the debris, looking for that one golden needle.
And that unimaginable global effort culminated in ultimate triumph on July 4th, 2012, when the discovery of the Higgs boson was finally announced to the world.
A huge day for science.
But smashing those particles together to find the Higgs didn't just prove old theories, though. It routinely created something that opens up an entirely new existential mystery. We need to transition from the Higgs field into the realm of antimatter.
Ah, yes, this is where the history of physics reads a bit like science fiction.
It really does.
Because antimatter was predicted entirely by mathematics before it was ever seen. In 1928, Paul Dirac was solving equations to merge quantum mechanics and relativity. And when you solve certain algebraic equations, the math essentially spits out a square root with both a positive and a negative answer.
Right, like algebra class.
Exactly. But instead of throwing out the negative answer as just a mathematical quirk, Dirac trusted the math. He predicted there must be a twin for the electron with an opposite charge.
And 4 years later, physicists found that exact particle, the positron, in the real world.
They did.
And Fermilab actually used to manufacture antiprotons. But it is a brutally difficult process.
Extreme.
You have to smash 100,000 regular protons into a target just to get a single antiproton out of the wreckage. They were running this massive facility around the clock, and they were generating about 1 nanogram of antimatter per year. A billionth of a gram.
The cost of that process is staggering, too. NASA has estimated that to intentionally manufacture a single gram of antimatter using our current technology, it would cost roughly $62 trillion.
Wait, 62 trillion? It is difficult to even wrap my head around that scale. $62 trillion for a paperclip's weight of material?
I know, it's wild.
And the reason it takes so much energy to make is because antimatter is basically concentrated explosive power.
Exactly.
If a single gram of antimatter collides with a single gram of normal matter, they completely annihilate each other, converting 100% of their mass back into pure energy. That 1 gram interaction would release the explosive energy of the Hiroshima and Nagasaki atomic bombs combined.
But the real mystery of antimatter isn't weapons or futuristic space propulsion. It is our very existence.
How so?
According to the foundational laws of physics, the intense energy of the Big Bang should have created exactly equal amounts of matter and antimatter.
Exactly equal. Meaning as the universe was born, every particle of matter should have immediately collided with a particle of antimatter.
Right.
They should have all annihilated each other, leaving a universe filled with absolutely nothing but glowing light, no stars, no planets, no carbon, no us.
Yet, against all mathematical odds, we are here.
So what does this all mean? It's like a rigged cosmic casino game. For some completely unknown reason, for every billion antimatter particles that were created in the Big Bang, there were 1,000,001 matter particles.
Just that tiny imbalance.
Right. The billions annihilated each other. And that one tiny leftover fraction of a percent is everything we see in the universe today. Why did regular matter win by exactly one extra chip out of a billion?
Physicists refer to the processes that generated this imbalance as barygenesis, or leptogenesis, basically, the origin mechanics of regular matter.
Okay.
And right now, there is a massive race between Fermilab and a team in Japan to study neutrinos. These are, as the intense heat of the early universe rapidly expanded and cooled, this wobble would mean that slightly more antimatter decayed or converted into regular matter than the reverse.
Oh, wow.
It could be the exact mechanical loophole that allowed regular matter to build up that tiny 1 in a billion surplus. It could explain why you, the Earth, and the stars exist at all instead of just empty space.
But even if we figure out the exact mechanical loophole that allowed regular matter to survive the Big Bang, we immediately hit a much more humbling reality.
Which is?
Everything we just talked about, the stars, the planets, the galaxies, you and me makes up only a tiny fraction of a percent of the universe. The vast majority of reality is completely dark.
Yes. We're stepping into the realm of dark matter and dark energy.
Let's start with dark matter.
Right. When astronomers look at galaxies spinning, they spin way too fast. Based on the visible stuff, the stars and the gas clouds, there simply isn't enough gravity to hold them together at those speeds.
They should be flying apart.
The outer edges should physically scatter into the void.
But they don't. Which led to the theory that there must be massive, invisible clouds of subatomic particles, dark matter, adding extra gravity and holding it all together.
Exactly.
But I have to push back on this assumption.
Okay, lay it on me.
If dark matter is supposed to be 5 times more prevalent than normal stuff, and we have been looking for it for 30 years with giant detectors buried deep underground, and we're smashing particles in colliders hoping it pops out, and we found exactly 0. Isn't it time to admit that maybe our math is just wrong?
That's a common thought.
Like maybe Newton's laws of gravity need a fundamental tweak on a galactic scale.
It's a very fair challenge, and many prominent physicists felt exactly that way for a long time. But this is where the beauty of observational science comes in.
What did they see?
Astronomers discovered something called the dragonfly galaxies. These are incredibly faint, diffuse galaxies that, when we map their rotation, perfectly obey Newton's laws of gravity.
Really?
Yes. They rotate exactly as they should based only on their visible mass.
Meaning they have no dark matter at all.
Exactly. And if our fundamental math or laws of gravity were wrong, they would be wrong everywhere in the universe.
See.
But because we found a galaxy where the dark matter has somehow been stripped away or never formed, it proves that dark matter is a physical, removable substance. It isn't a math error. We just haven't figured out its exact mass or how to build a sensitive enough detector to catch it yet.
Okay, so that's the dark matter holding galaxies together. But then in 1998, observing the universe got even stranger.
Much stranger.
Scientists were looking at the expansion of the cosmos, fully expecting it to be slowing down because the collective gravity of all the galaxies should be pulling everything back together.
Right.
Instead, they realized the expansion of the universe is actually accelerating. It is actively speeding up.
Which points to the existence of some kind of repulsive force pushing the fabric of the universe apart. We call it dark energy. And ironically, Einstein actually predicted this. He added a cosmological constant to his early equations to balance the universe, then called it his greatest blunder when Edwin Hubble discovered the universe was expanding.
But it wasn't a blunder.
No, it turns out Einstein's blunder was right all along. That constant represents dark energy.
But calculating the nature of dark energy has led to what Don Lincoln calls the worst prediction in physics.
Oh, yeah. It's notoriously bad.
Because quantum field theory tells us that empty space is actually boiling with microscopic quantum fluctuations.
Yeah.
Particles popping in and out of existence.
Right.
If you add up all the energy from those theoretical vibrations, that total is called vacuum energy. But when physicists calculate how much vacuum energy should be pushing the universe apart and compare it to the dark energy we actually measure, the prediction is off by a factor of 10 to the 120th power.
It's almost comical.
That is a 1 with 120 zeros behind it.
Yeah.
To say the math is spectacularly, embarrassingly wrong doesn't quite capture the scale of the error.
No, it doesn't. And this raises an important question for the field. With such glaring holes in our knowledge, we don't know what dark matter is. Dark energy calculations are off by 120 orders of magnitude, and gravity completely refuses to play nice with the quantum mechanics of the other three forces. Where do we go from here?
Physicists are desperately hunting for a theory of everything, or a ToE. They want to finish Einstein's unfinished dream of unifying all four forces into a single framework.
Right, the ultimate unification.
You hear a lot of pop science about string theory, which suggests subatomic particles are actually vibrating microscopic strings, or loop quantum gravity, which suggests space itself is pixelated into indivisible chunks. But are we getting way ahead of ourselves with these theories?
Well, Don Lincoln maintains a very pragmatic, skeptical view of this pursuit.
Why is that?
Because the mathematical energy scales required to actually test string theory are a quadrillion times higher than the colliders we have today.
A quadrillion.
A quadrillion. That is 10 to the 15th power. We simply cannot build a machine large enough to test it.
Don has this brilliant analogy to put that limitation into perspective. Imagine an Australopithecus, an early human ancestor, walking around the savannas of Africa a million years ago.
Okay.
They know their local environment. They can predict what is a mile away. But imagine asking them to predict the existence of deep-sea sperm whales, or the freezing snow-capped Alps, or penguins in Antarctica.
They couldn't possibly do it.
Right. Their local rules don't apply to those extreme environments. So aren't string theorists basically just guessing what a penguin looks like without ever leaving the savannah?
That is a very sharp critique, but it connects back to the core values of the scientific method. You can invent the most beautiful, elegant math in the world, like string theories, multiverse landscapes, but it is fundamentally useless to science without a testable, falsifiable prediction.
Yeah, you have to be able to test it.
Progress will not come from top-down, elegant math that we won't be able to physically test for centuries.
Wow.
Real, practical progress is going to come from the messy, local anomalies. It comes from the, that's weird, moments in our current experiments.
Like the dragonfly galaxies, or the neutrino oscillations.
Exactly, those weird little moments.
Let's take a breath and look at the journey we've just been on. We started with Isaac Newton watching an apple fall, or you dropping a sandwich, and we followed that human urge to unify the rules of nature.
It's been quite a path.
That urge led us to realize that space and time are the same fabric. It led us to discover the invisible Higgs field that gives us mass by bogging down heavy particles. It drove us to build machines the size of cathedrals to smash matter into pure energy, revealing antimatter, and the 1 in a billion rigged casino that allowed matter to survive the Big Bang.
And it ultimately forced us to realize that everything we have just described, the entirety of human experience in visible matter, is just a tiny fraction of a universe dominated by completely unknown dark matter and an accelerating, repulsive dark energy.
You can feel incredibly abstract when we talk about a quadrillion times our current energy limits. But it is that exact urge to poke, to prod, to shake the universe and figure out the mechanical rules that fundamentally makes us human.
Absolutely.
And eventually, those esoteric rules become the technologies that run our modern world.
I want to leave you with one final mind-bending thought to mull over, specifically regarding the mechanics of dark energy.
Oh, okay. Let's hear it.
We established that the universe is expanding and that expansion is accelerating. But the weirdest thing about dark energy is that its density seems to remain constant even as the volume of the universe increases.
Wait, how is that possible?
Right. Think about it for a second. If you stretch a rubber band, the material gets thinner. But if space is expanding and the energy density stays exactly the same, it suggests space isn't stretching at all.
Then what is it doing?
It suggests that space itself is quantized. Imagine that microscopically tiny, Planck-sized bubbles of space are continuously popping into existence.
Bubbles of space.
Yeah. Right now, in the very room you are sitting in, reality itself might be foaming into existence, generating new pockets of space right in front of you to drive the expansion of the cosmos.
Just a little light thinking for your day. Thank you so much for coming on this deep dive with us. We hope you feel a little more well-informed and maybe a little more in awe of the invisible machinery running the world.
It's been a pleasure.
So the next time you trip and drop a sandwich, don't just curse terrestrial gravity. Take a second to appreciate the foaming, Higgs-laden, matter-dominated space-time fabric that caught it. See you next time.